Hello, everyone. A very good afternoon to everyone. I welcome you all to the week 12 of problem solving session for the course Ultrafast Laser Spectroscopy. So, as the previous weeks, we'll follow the same thing that we'll be solving few questions which will be related to the questions or the assignment questions given in the week 12 assignment. And then further, if you some problems or doubts more than that regarding the questions, we'll be solving those also. So far, as I can see, no one has joined. So first of all, we'll just wait for some time to let people join, and then we'll continue the session. Before that, I'll be presenting my screen so that all the questions are visible to you. Okay, so now we'll start solving the questions. So first of all, in this week, I'll just give a quick review of the topics, whatever we had discussed. The first topic was bi-exciton, how it is generated, or not bi-exciton. Basically, that was multi-exciton generation. Okay, and then so far we had studied that when you irradiate some system with light, then an electron moves to a higher energy shell, and therefore this pair of an electron and the new hole that is generated due to the excitation of electron, this whole pair is called the exciton. Now, see, in the earlier cases we studied that only single photons are generated generally, but single exciton is generated from a single photon. But now we know that yes, there is a process called multi-exciton generation. How the process is useful, where that is used, and the second topic that is of also very importance, that is of 2D IR or 2D infrared spectroscopy. So starting with this, first we'll discuss the first question. Now, what they have asked us in the first question is, question 1 says bi-exciton generation. Now, first of all, before starting this, first we'll discuss what is a bi-exciton. Okay. Yeah. So, the name suggests something that is related to the excited state. Okay. So, bi-exciton is generation of two excitons. Okay. Now, what is an exciton? Exciton is an electron hole pair. Okay. Now, see, uh, generally we categorize the materials into three categories based on their conduction. The first is conductors. The second is semiconductors. And the third is insulator. And we have studied in our earlier classes from school level that the band gap denoted by Eg is least, is more, and maximum in case of insulator. And that is why they cannot, or they are unable to conduct electrons. Okay. That is why they work as the insulators. Now here what we are talking about is, now suppose in a system you have irradiated a light. Generally what happens, say the electron is, this is in the form of pair. This is the singlet ground state. Now what happens, you have irradiated with light of some frequency. One of the electrons, say this one, will reach to a higher state with this same multiplicity. Okay. Now what will happen here? There will be one hole generated and one electron will reach to a higher level. This excited electron and this hole, they together form exciton. What we are talking about. Okay. Why is this bi-exciton point of interest? Because normally when you say if a system is irradiated with one photon, only one exciton is generated. And these excitons then are working as the charge carriers in the system. Now suppose you attain a situation where you do not get single exciton but you get more excitons, and thus you have more charge carriers. So here they have written that there is a condition. Not in every condition there you will generate a bi-exciton. There is a condition that the amount of light incident on the sample, that h nu should be greater than Eg. Or you can say H nu should be greater than twice of Eg or thrice of Eg. What is this Eg? This Eg is band gap. Now here again this can be explained with this diagram, this graph. Now say this is the absorbance. Now see here 1, and it is absorbance is plotted against the x-axis E upon Eg. So E stands for the energy which is supplied. Okay, stands for the energy which is supplied. Okay, or supplied, not energy which is given. Now at the E is equals to Eg, the normal case where say this is an electron in this shell and it is excited to the higher level, you will get a single peak. Okay, so this is band age absorption. Now next what can happen? Next can be the other case. The other case can be when the energy of this photon is greater than the band gap energy. Now what you will get is this electron which will reach to a higher energy state will have some extra energy with it. And that is why this exciton is called as the hot exciton. So here I'll just write what is an hot exciton. Hot exciton the exciton which has energy greater than the band. Okay. Now, now see this phenomenon of bi-exciton generation. How does it take place? You have a system, say this one. You have incidental light of frequency of energy h nu. Then electron from the ground state reaches to the first excited state, say this one. Then further what happens, this hot exciton with some amount of probe energy, it excites one more electron from the ground state. As soon as this electron is excited to the higher state, see there is generation of two high energy electrons generating two holes, and this is called as the bi-exciton. Now, it's not necessary that this bi-exciton will be as it is. It will undergo Auger recombination, which is again a process of the recombination of electron and hole. Further, there you will get a single exciton which has a higher energy. In this spectra, you can see there is a condition, say if E is greater than Eg, then necessarily the value will be greater than 1. And you will see there are small peaks coming at some places. What do these peaks indicate? These peaks indicate that there is some sort of absorbance happening at this position. And if the absorbance is happening, therefore the bi-exciton generation will happen. Definitely. Now, see, this whole process of bi-exciton generation is not depend or is not does not happen at 100% probability. Like there are chances it will happen, or there are chances it may not. There are other processes also which we have studied. For example, internal conversion, intersystem crossing, fluorescence, phosphorescence, any non-radiative or radiative decay which are accompanied by this bi-exciton generation. This bi-exciton may further recombine with the electron and will not form, sorry, this single hot exciton generation generated may then, it may also happen that it will combine with the electron, release the extra energy, and there will be no bi-exciton formation happening. Okay. So, the point of interest here is how the bi-exciton will be generated. So, first of all, the condition for bi-exciton generation is the pump beam intensity should be maintained low. Why is it necessary? Because the more is the pump beam intensity, the more will be the loss. And if more loss is happening, bi-exciton formation will not happen or will be affected drastically. Okay. Now, in the case of bi-exciton formation, two excitons are generated. Okay. Then, second thing is, how on what parameters does the bi-exciton formation depends? Only the condition if the frequency of the incident light or the pump light is greater than the band gap. In that case only bi-exciton generation will happen. Okay. So here we can also say that the second factor is the wavelength. The wavelength or the energy of the energy of pump beam. So these are two factors which are very much necessary to be considered. If you want a bi-exciton to be formed, you need these two parameters to be considered. The first is the pump beam intensity should be maintained low. Okay. The second is the wavelength of the energy wavelength or energy of the pump beam is also a factor. Now wavelength is directly that is controlled that also affects the color. That is why in the case of bi-exciton formation, we have two options that are correct. The first one is require high intensity of beam. Second is takes place by merger of two excitons. No. In this, two excitons are rather generated and not merged. Is sometimes followed by emission from S2 state. So no. In the case of bi-exciton formation, the excess energy that this hot exciton possesses, that is given to the another electron to get excited to a higher level. It also depends on the color of the pump. Okay. So, thus, now I'll just repeat all the things which I told. The first thing is, say, what is a bi-exciton? So, similar to exciton, if two excitons are generated at a time, they are called as a bi-exciton. Okay. The first thing to know. Now, how is this generated? Bi-exciton is not generated in normal cases. You need a pump beam that has quite high value of, say, the wave energy compared to the band gap. If it is twice, then only say this hot exciton will have any surplus amount of energy which it can give to excite the another electron. What happens is this electron which has some extra energy, it gives to the bottom electron that is in the lower level. The other electron raises, then moves to the higher energy state. Similarly, a new hole is generated. When these two holes and two electrons are there, these two pairs are called bi-exciton each. Now, followed by this bi-exciton formation, the process may so happen that one of the bi-excitons, it may recombine, and thus the single exciton which will remain that has some higher energy compared to that. When you study this graph, you will get to know that there, apart from when you plot the absorbance as a function of E by Eg, you will see that when E is equal to Eg, that is E upon Eg is equals to 1. In that case, you will notice an absorption. So that is the normal transition which we studied from HOMO to LUMO. In the other cases, if you supply or if the energy provided to the system is quite greater than the band gap energy, there will be further absorption happening at the other stages. And this absorption states that there is some amount of energy that is still absorbed by the system which is used for the bi-exciton generation. Okay. Now, in this, there are few new terms also which we have discussed. What is an hot exciton? And hot exciton is the exciton which has energy which is greater than the band gap. Okay. What is an exciton? An exciton is an electron hole pair. What is a single exciton? Which is formed by the system when it undergoes recombination. Then there were two parameters that were very important for the bi-exciton to be generated. As I said, there's not necessary that only bi-exciton will be generated if a system is provided with the surplus energy. There are chances that apart from the bi-exciton formation, it may so happen that the system may lose the energy in the form of radiative or non-radiative decay. Okay. Now, in order to reduce the probability of these processes happening and increase the probability of formation of bi-exciton, there are two conditions necessary. The first one is uh, it requires a high intensity of no, it does not require high intensity of pump beam. It requires a low intensity of pump beam, and the only option correct is depends on the color of the pump light. Okay. So for the so I just mark this as right, but this is not a right answer. Low intensity of beam is required for the pump beam, and it depends on the color of the pump light. Okay. Uh, Now, if you have any doubt, just ask, or else we'll proceed to the next question. Okay. So we'll go to the next question. The second question is why exciton can be used to achieve. See, uh, the bi-exciton, why is it necessary to be generated, or why we are studying the process of this formation of bi-exciton? So we'll just take a look of the process, what happens after the bi-exciton is generated, and including how the bi-exciton is generated. Okay. So consider this is a system. Okay. The first thing that happens after photoexcitation with the light greater than the band gap energy is at time zero, the electron reaches to a higher energy state, leaving back a hole in the ground, in the in the uh, HOMO. Then what happens? See, there are four systems given. Okay. In each case, the same processes happen. Now, what happens? There are two processes. First is the impact ionization. Impact ionization means the excess energy when given to the system. Then what happens? This higher energy electron, it comes to the say the lower state for leading to the formation of new excited electron. Okay, so if you consider a system with say 100 molecules, then here the chance of impact ionization to happen is 50%. And the second thing is chance for the recombination and pooling is also 50%. So basically, if you excite a system, it's not sure that the system that in that bi-exciton will be generated necessarily. It may so happen that some bi-excitons are generated while the other they relax or recombine, releasing the excess amount of energy. So these are the two processes. After that, after cooling, there is nothing left. Now, these bi-excitons may then recombine, and thus only single exciton may be left, which is the again a process that takes place with a function of time. say in very small scale or ultra fast time scale. Okay. Now, why is this whole thing we are studying? Because when this process happens of bi-exciton generation, it you generate from a single, say from a single photon, only one excite only one exciton is generated, which leads to the formation of two excitons. So this is just the twice that is happening, which does not happen in a normal case. In the ideal case we consider that a single photon generates a single exciton. Okay, but here in this case, two excitons are generated from single photon, and thus the number of charge carriers increase. And what if these recombine and on cooling they emit fluorescence? Then in that case, the number of photons is multiplied. Okay. Now here also there are two foremost important point to be discussed. The first case is the conclusion which we got from this is, first, in bi-exciton formation, the efficiency of a system is never 100%. Second thing is, there are other processes which go on with this process. They are the other non-radiative pathways. Okay. And thus, the third point is, bi-excitons are extensively used in Now, coming to the solution of our question, they asked, biexciton can be used to achieve. See, answer to this question is quite easy because so far whatever we have studied, biexciton cannot be used to generate second harmonic generation. Second thing is saturable absorption, which we had studied, there that are used that use the rhodamine 6D dye and the other dyes. That can also not is not also not the true answer. The third option was white light generation. So these three options are not at all correct because they never go on with the uh, whatever biexciton generation process. Although in the third case, the option that is given is multiplication of the number of photons. So yes, from a single photon, the number that is generated, that is quite high. So thus, the multiplication of the number of photons happens. But somewhere, if we consider second harmonic generation, then in second harmonic generation, we used to consider that the wavelength is reduced to half or the frequency is doubled. But in this case, no change in those happens, although the number of photons, they increase. Okay. So I'll just repeat in a quick time whatever we have discussed. Biexcitons can be used to generate photoexcitation. Sorry, when the biexcitons are generated, photoexcitation happens. The photoexcitation, the light incident on the sample is quite high compared to the band gap. Followed by this, there are two processes happening simultaneously. That are the impact ionization and cooling. Case of impact ionization, one another electron is used to ionize the other electron from the ground state and thus lead to the formation of biexcite. There is another process of cooling that goes on simultaneously with this after this photoexcitation, where the electron and hole recombine and thus cause cooling. The energy excess is lost in the form of non-radiative decay. The third thing that happens is after followed by this impact ionization, maybe these biexcitons, one of them they can recombine to by Auger recombination and thus form a single exciton of higher energy. Okay. So far the for the question 2, this last is the answer. Now we'll go on to the question number 3. In the question number 3, they asked, in the experiments of Nozick and co-workers, the efficiency of charge carrier generation is found to be. Okay. So, see, each one. Basically, in semiconductors, the band gap is less than insulators. Okay. First point. Now, when talking about EG, band gap energy, then for then the smaller the size of the particle, the lesser is the band gap. So, as you know, I told that there is a certain amount of band gap EG. Okay. Now, within this EG, if you talk about the bulk state, if this EG is also high, and if this EG is high, then in that case, uh, like there will be another processes which will be followed in the case of bulk, or which will be happening in the case of bulk. Okay. The other case, in the nano case, in case of nano level particles or quantum dots, the band gap is less. The lesser the band gap, the more are the chances of bi-exciton formation. Although the efficiency is never 100%. These materials they find application in making of what? In making of solar cells. Okay. So in the experiments of Nozick and co-workers, the efficiency of charge carrier generation is found to be, in case of this QD stands for, what does this QD stand for? QD stands for quantum dots, and PBSE is a semiconductor. Okay. Now, what I discussed, what are the points to remember here? The points to remember are, first, semiconductors, the band gap is less than in case of insulators. When we talk about the band gap, the smaller is the size, the lesser is the band gap. The lesser is the band gap, the better is the bi-exciton generation. In nano levels or quantum dots, the band gap is still less, and this lesser gap persuades the formation of bi-exciton. QD here of PBSE has a higher efficiency than compared to the bulk PBSE. So when you talk about the efficiency of charge carrier generation, which also depends on this bi-exciton formation, in any case, whether in bulk or PBSE, it can never be 100% because all the other processes happen simultaneously. But we can just say that in case of bulk, whatever the efficiency of charge carrier generation is, compared to that, in case of quantum dots, the efficiency is more. So our answer would be more in PBSE QDs and then bulk PBSE. Okay. So yeah, first we saw in the experiments of Nozick and co-workers the efficiency of charge generation. They compared it using two values, the bulk and PBSE, with the quantum yield and the h nu by E, which is the energy supplied versus the band gap. When they see as the energy supplied is increased in case of bulk and quantum dots both, in the case of quantum dots, the slope is high. In case of quantum dots, also the quantum yield is also high. Compared to that in the bulk PBSE, the slope is less, and thus you can say that yes, in that case, the efficiency for charge generation is also so more in PBSE quantum dots than bulk PBSE. This is the answer to this question. If you have any doubts, just ask, or else we'll go to the next question. Okay. So question number 4 asks two peaks in the IR spectrum. The options given are necessarily imply two isolated modes, necessarily imply two coupled modes, may be observed in may be observed for isolated and coupled modes, or indicates the presence of impurity. In order to discuss this, we just see how we get the two peaks in the IR spectrum. Okay. So in the infrared range of the spectrum, we normally consider the vibration of bonds. And for this, we consider the simple harmonic oscillator model is considered. Okay. Now see, in the IR spectrum, normally you see there is a single peak, but in sometimes of molecules, say of N single bond O, double bond O, you get coupled, you get two peaks. Okay. Now the two peaks, one is for the say symmetric mode, and the second one is of the asymmetric mode. This is a different case. There is another case where the two vibration modes are not in contact to each other directly. But the vibration of one mode affects the vibration of other. Okay. So basically, yeah, there are chances that you get coupled modes, you get isolated modes, but looking at 1D IR or the normal IR spectrum can never say that the mode is isolated or coupled. Okay. To look at closely, at if the mode is coupled or not, we have to do 2D IR. Okay. In this 2D IR, it will be more clear if the two modes are coupled or if they are not, or what is happening. Okay. Now, two peaks in the IR spectrum, we got to know from here that yes, you get two peaks in the IR spectrum. Maybe they can be isolated, they can be coupled. But how to judge or how to find out if they are coupled or not is 1D NMR is insufficient to do that. You need 2D IR, sorry, 1D IR is insufficient to do that. You need 2D IR techniques to just find out whether the two modes are coupled or not. Okay. Now, These two peaks, in the case of intermolecular interaction within the molecule interaction, this can happen. But there can be still another case. In the other case, you have, say, a molecule with NO2 group and an OH. Necessarily, these two will interact, and when these two will interact, you will get or give the rise of coupled vibrations. Okay. Now, I'll just write it in some good handwriting. So, you cannot say that the two modes are necessarily isolated. You cannot say that the two are coupled. You cannot say that there is an impurity present, but you can definitely say that in case of IR spectrum, if you observe two peaks, they can be separate from each other. They can be unrelated to each other or uncoupled to each other. It's not necessary that they are arising from the same molecule or from the same atoms. Now we'll go on to the next question. The next question is 2D IR spectrum of two uncoupled non-degenerate normal modes would have. Okay. So what is this 2D IR? See, what they have asked? Two uncoupled non-degenerate modes. See, first of all, to draw the energy diagram of one mode in the case of simple harmonic oscillator, we draw something like this, where V is equals to 0 is the ground level, V is equals to 1, and as the anharmonicity increases, the band gap between each reduces, and this is V equals to 2. So this is what is seen in the case of one simple harmonic oscillator, which represents one vibrational bond. Now there is another case where they have two bonds nearby. So how you can draw the two-way structure? The two-way structure can be drawn like this. Here 0, 1, 2 and 0 prime, 1 prime and 2 prime are the levels. Okay. Now see what has happened. Now we want to look of how the two uncoupled modes will look in the case of 2D IR spectrum. So there are few processes, say 1, 2, 3, 4, 5, 6. Wait a time of 2 minutes. I'll just clear this. Okay. So, see, there are two isolated modes. As we know, 0, 1, 2 are the vibrational levels, and 0 prime, 1 prime, 2 prime are the vibrational level of the two modes. Now, suppose this you have named it as mode 1 and mode 2. Okay. Now, in this mode 1, initially you are incidenting it with some light that is equal to the band gap between these two levels. Okay. What happens? First of all, the absorption will happen. the ground state population, it will reach to a higher energy state 1. Okay. Now see, there is one more process. Now suppose this is the pump beam. Okay. From here onwards, we'll study each of the following case in case of pump and probe. Now this is the pump beam. You incident it, it will reach to the higher state. Now you incident it with second with a probe beam. Okay. Now probe frequency, let's say it is equal to that of the mode 1. Now, if the probe frequency is equal to that of the mode 1, the first thing that will happen is that of the stimulated emission. So, along with the first, which is the absorption, the second is the stimulated emission that will happen. Now, along with the stimulated emission, there is one more thing that can happen. Suppose the pump probe frequency is lesser, then in that case, the population which is on the higher state of V is equals to 1 will again gain the energy and reach to the higher state V2. So, this is just the absorption. Okay. Now, along with the stimulated emission, what I was talking about, the third thing that, or not the third, the fourth thing that is involved is the ground state bleach. Now, say, in any worst case, the ground state population can never be zero. Suppose you are on the system, you are just using the probe frequency that has equal intensity to that of the pump beam. What will happen? Few electrons in the system, few state, if the system, most of the state, that is the ground state is populated, some of the population will again come to a higher state, and that is called as the ground state bleach. Okay. Now, in this case of the ground state bleach, you will notice that, you will get a negative peak of absorption, say like this. Okay. For the case of absorption or the stimulated emission and the ground state bleach, you will get a negative peak, while for the absorption, you will get a positive peak. Okay. Now, when you just plot it on the 2D curve, say in the 2D curve, this is the mode 1, this is the mode 1 with mode 2 and mode 2. See here carefully. On the x-axis, there is probe frequency. The probe frequency value is different from each other. That is the mode 1 and mode 2, mode 1 and mode 2. Now, in the first case, where these are two isolated modes, but they are together, not connected to each other, but if you incident the one pump beam along with it, you get two processes happening, the 2 and 3. Similarly, if you consider the other system of mode 2, where you use the pump frequency of mode 2 only, then in that case, the three similar cases which you observed in case of mode 1 will be repeated. Okay. So 1, 2, 3, 4, 5, 6. Okay. In case of 1 and 2, in case of 1, 2, what you get a negative peak. In case of 4 and 5, you get a negative peak. Interesting point is both the peaks or positive or negative peak are on diagonal peaks. Both the peaks 1, 2 and 4, 5. And something that is over this axis is required to plot a contour diagram. Then the case of 6th and 3rd, the 3rd, 6th, they give a, what do they give? They give a positive peak, but the peak is off diagonal. Okay. But in this case, the peak will be off diagonal. Now, this is the first case and the simplest case where we have considered modes which are isolated from each other. Now, as soon as you incident the light of frequency that is equal to the band gap in case of mode 1, immediately mode 1 will absorb that energy, reach to the higher state, although there's still some population in the ground state. Also, when after irradiation, if you use the probe frequency that is a value equal to that of the pump beam, then in that case, stimulated emission and ground state bleach will happen. What does stimulated emission means? Where a single photon is used to stimulate the entire emission. The second case is ground state bleach, where the population in the ground state will try to reach to higher state and therefore you get a negative absorbance. Now, the third case would be this 3, which is denoted by 3. And in this case of 3, what will happen? If the probe frequency has certainly lower value than that of the pump beam, then the system will gain sufficient amount of energy to reach to the third state. Two isolated bands are not shown by connection to each other, but they are shown in a separate way in the form of wells. Then if you plot a 2D contour diagram of mode 1 and mode 2, you will get, in case of mode 1 to mode 2, you get a negative peak with which is on diagonal. In case of mode 2, in case of the third and sixth, you are always getting a positive peak, and that too, which is off the diagonal. Okay. So here we come to the solution. The 2D IR spectrum of two uncoupled non-degenerate normal modes is two uncoupled. First of all, they are not coupled and they are non-degenerate normal modes. So you will get one peak, one peak, one peak, and one peak. This is for A and this is for. Okay. So uncoupled non-degenerate modes will generate what they will generate? Two positive and two negative peaks. Okay. So you cannot write two positive peaks, two negative peaks, or a positive and negative. You can write two positive, two sets of positive and negative peak features. Remember, this is for the two uncoupled modes. If you are talking about a single uncoupled mode, then you will get a positive and negative peak. Okay. If you have any doubt, just ask, or else we'll go on to the next question. Okay, so now we'll go to the next question. The next question is the 2D IR spectrum of normal mode would have. See, the first case which we discussed was two uncoupled normal modes. Now here we are discussing one normal mode which is simply a normal mode. Now, in this case, the case would be a simple one. In this, the first one says 0, 1, 2. Okay, these are the vibrational levels, the ground state. The first one is the absorption. The second one would be stimulated emission for along with the ground state bleach. These together will give a negative peak for when the pump beam is irradiated. And the second thing is the third, that is the absorption, which will again give a positive peak. Okay. So this first, second, what do they do? The first plus second, they give a negative peak, and the third one gives a positive peak. So the answer would be a positive and a negative feature. Okay. So a normal mode involves three processes. The first is transient absorption. The second one is stimulated emission. Third is the absorption and or transition from V is equals to 1 to V is equals to 2. Okay. So answer is a positive and a negative. Okay. Is there any doubt? Okay. So now we'll go on to the next question. That is question number 7. Yeah. So this will be the diagram where the pump frequency and the probe frequency are something. The pump frequency equal to the gap between or the energy gap between 0 and 1. With this as the pump frequency, if you apply a probe frequency with a value 0, 1, then you will get 1 plus 2 peak. If you apply something that is less than that, then you will get 1 plus 0. Okay. Then uh, for those all the experiments, the pump probe technique is used. Okay. Now we'll go on to the next question. Question number 7. So far, whatever we have discussed in the questions, the first one was bi-exciton generation. Bi-exciton generation refers to when two excitons are generated from a single photon. The process is quite simple. The only condition necessary is the energy or the beam should be of high energy. It should possess energy h nu greater than 2 times of the band gap or 3 times of the band gap. Leads to the formation of an hot exciton, which therefore excites another electron and forms a bi-exciton. The bi-exciton then recombines with via Auger recombination to give a single exciton. The only condition that is important for bi-exciton generation is the pump beam intensity should be maintained low, and the wavelength of the beam, that also matters. You should use a high energy wave. Okay. Then from the graph also we studied, if you are getting more peaks other than that of when E is equals to Eg, the other values indicate that there is further absorption happening in the system, which may be an indicator of bi-exciton generation. Then bi-excitons are also source of generation of charge carriers. Why is these charge carriers necessary? These charge carriers are necessary in the formation of solar cells. Okay. Now, yeah, the efficiency to form a bi-exciton is never 100% in the whole process. And there are another processes, non-radiative, radiative decays that continue with it. So therefore, bi-excitons can be used to achieve multiple number of photons, multiplication of the number of photons. Then in this question, there are two other processes which will also be studied, that followed by the bi-exciton followed by the photoexcitation. How the bi-exciton is formed, that is formed by the impact ionization, where 50% of population after excitation may undergo cooling, but the rest 50% is still capable of achieving the impact ionization and generating a bi-exciton. The bi-exciton then recombines and gives the formation by order recombination, and the cooling happens. Okay. Now this is the question number 2. Now the next one would be question number 3. In the question number 3 also, question number 3 also, in the question number 3 was an experiment that was done by Nozick and co-workers to look after what is the efficiency of charge carriers when you talk about the same material, but it is in bulk or at a nano level. So we found out that the band gap directly depends on the size of the atom. In case of bulk, the band gap is more, and thus in case of the quantum dots or the nano level particles, the band gap is less. The lesser will be the band gap, or the lesser will be the size of the particle, the better will be the formation of bi-exciton. Although since we studied that the bi-exciton generation does not occur at a rate of 100% conversion, but still if the bi-excitons are formed, they are formed in a better way in case of if the system is of nanoscale. So therefore, quantum dots here in this case have quite higher efficiency than the bulk lead selenide particles. Okay. So the answer to this question was the charge carrier generation efficiency is more in case of quantum dots and not in case of the bulk gases. Next, we had discussed two peaks in the IR spectrum. So necessarily, this is the next topic that was important discussed in the week 12. The IR spectrum comprises of lots of peaks. They may be connected to each other, not connected to each other, but still they give peak. Now, from the 1D IR which we normally see, we cannot distinguish if the two modes are coupled or not, if they are isolated or not. These all the things they are determined when you go to the further advanced technique, that is the 2D IR spectroscopy. In case of 2D IR spectroscopy, if two of the modes they are related to each other, they are not isolated but are not not coupled or coupled and not isolated modes, then in that case we can easily find out this, and that I'll be telling you later. The first case was of 2D uncoupled non-degenerate normal modes. See if coupling is happening or not. What do these non-degenerate normal modes mean? That the energy gap between the two modes for the each level is not same. When we consider the case in mode 1, some amount of absorption is happening from ground state population reaching to higher state. Similarly, stimulated emission is happening. Similarly, there is a third case when the probe frequency is lesser than the mode 1 frequency. Then in that case, that from 1 to 2, the population will go. In the first case of 1 and 2, you'll get a negative peak. In the case of 3, you'll get a positive peak. This is indicated in this diagram by this. Okay. In the other case of mode 1 and mode 2, say this is the case, similar thing will happen, but now you are using a pump beam which the frequency that is equal to the band gap in mode 2. In this case also, you'll get the same process is happening. The only difference is this is a mode 2 with a lower wave number. Okay. Now, how many peaks so far you got? So far you got that there are two peaks which lie on diagonal and these are the negative peaks while the other two neighboring peaks are the positive peaks. Thus, and how are these peaks arising? These peaks are arising due to these modes. Okay. These two modes give a negative peak. These two modes give a positive. Now, the non-degenerate normal modes would have two sets of positive and negative features, a positive and a negative. So when you talk about two degenerate modes, you need to talk about that each one will give two sets and therefore two sets of positive and negative features. So this is the answer. Okay. Next, we'll go to the next question which we had discussed, question number 6. Now they have given a normal mode. In the normal mode, they have given 0, 1, 2. In the case of 0, 1, 2, they said that positive and negative feature. Why does it happen? A positive feature is because of the absorption from 1 to 2. The negative feature is due to the transient absorption. And the second, the ground state bleach. The third is the stimulated emission. Okay, so in case of emission, there is no absorbance happening, and similarly, a ground state bleach is also happening, so you get a negative peak and not a positive. Thus, from till here, we have completed 6 questions. Now, you'll go to the question number 7. Question number 7 is the 2D IR spectrum of two coupled non-degenerate normal modes. Okay. Now, see, 2D IR of two coupled non-degenerate normal modes. Why they are coupled now? Now, this is the real case for which we have done a total discussion. Why the 2D is useful in case of coupled mode. See, these two modes are there. These two are not coupled to each other. Now, how do you have given the nomenclature to each state? Say for the ground state for both, you have nomenclature, you have named it as 0, 0 prime. But in the first case, for the other level, you have for mode 1, you have reached a higher vibrational level, but mode 2 remains the same. Similarly, in this case, it reached to 2 and it reached to 0, 2. Okay. So, based on this, there is one more mode that is accompanying them and that is denoted by 1, 1 prime. Okay. Now, see here. Wait a second. Whenever the two modes are coupling, the coupled modes are represented by the diagram as such. In the coupled modes, they are like a double wave structure. Okay. Now, if you excite this system, necessarily because of the small barrier, some amount of energy or the transfer will happen to this state also. Okay. Now, in this case, you again use pump frequency, probe frequency for mode 1 and mode 2. Now, the case has become a bit more complicated. In the case of mode 1, say 1 is due to the absorption, second is due to the emission, the third is due to the absorption to the higher state, and the seventh is due to 1, 1 prime. Now, say you have excited 1. Okay, you have done this with pump frequency 1. Now, apart from 1 to going to 3, what is the other chance? From 1 to going to 3, there is yet another chance. That is 8. Okay. Now, from 1 to 0, the system will again absorb 1 photon. And from 1 photon, it can again go from 1, 0 to 1, 1 state also. Okay. And that is what happens. Along with 1, you will get 8. Okay. You will get 8 also. And this will happen if you incident it with a light of mode 1 frequency. The second case is if you excite it with mode 2 frequency. Now, suppose you have this one, you excite it with mode 2 frequency. Okay. Now, in this case, Uh, and no, yeah. In this case, it will reach to further higher level. Now, if one is over, now we'll discuss what about the fourth one. In case of 4 1, similar things happen. From 4 0 0, it reaches to 0 1. It may happen from if the probe frequency is high enough equal to the mode 1. Then in that case, from 0 1, it will go to 1 1. Okay. And this is how the both the rules are followed. Only single photon and only jump from one level to another where the plus minus is equal to 1. Okay. So this is the whole scene. When you plot each other by deriving the relationship between them, you will see that there are few peaks. Now see, these are the peaks that are in the direction of diagonal. So these are called the off diagonal peaks. So these off diagonal peaks appear only when, I'll just write here. So the answer to this question would be here. See, in this case, we got to know that there are two sets of odd and two sets of positive, two sets of negative odd even peaks. So two sets of off diagonal positive and negative. Okay, not all along the diagonal, but you get off the diagonal. That is the most important feature. Okay. Now, with question number 7, we'll go to the question number 8. The function of Fabry parrot interferometer in the frequency domain in 2D IR spectrum is 2. So every Fabry parrot filter, what it does? Fabry parrot filter is like a semi-reflecting mirrors of 2 that generate a cavity. As soon as the light enters inside, it will just go back to and forth within this cavity. Similarly, from here, also the same thing will happen, and thus what will happen at last? Some amount of light after partially reflectance comes. Okay. Now, this whole thing is used in order to increase or to scan a broad range of ground frequency. So this is the answer to this question. See, here the probe beam is directly going to the sample. In the second case, the pump, it goes straight and through the sample but reaches the spectrograph. Although the D, it is blocked on a way. Why is this D blocked and the purpose? You have to scan a broad range of frequency. It helps in that. Fabry parrot interferometer. Okay. Now we'll go on to the next question. After the bi-exciton formation, the processes involved are. So impact ionization and order recombination are the two important processes that happen after the formation. Bi-exciton has happened. First of all is, see from the picture, it is quite very clear that there is a gap between the two. There is a hot exciton. What happens to this hot exciton? It loses energy, comes to ground state. The energy left is used to excite the another atom. Okay. And as soon as this another electron is excited, it excites another electron also, and thus this order recombination happens. So the process involved in the bi-exciton formation are order recombination and impact ionization. Then, yeah, the fourth part of laser pulse in time-time domain is the local oscillator, and it is necessary to extract that data of the probe. The third is time depend to the IR spectroscopy. The 11th question and the last question for this assignment is a pulse pair is used as a pump in time-to-time domain to the IR tool. So what is the purpose of using a pulse pair there? So the pulse pair is in order to eliminate the for a probe or so as to strengthen the probe pulse. So it is used as its Fourier transform is a sinusoidal distribution of wavelength. So this is the right answer to this question. Okay. So now I have given certain assignment questions also, which we can discuss. Okay. So maybe the connection was lost. There was some problem. So we just discussed again the questions. Yeah. So till here we had discussed that this coupling it leads to the formation of new off diagonal peaks that happen because if you excite with some frequency that is of mode 1 and you use a probe frequency that has a different wavelength for mode 2, then you will get the off diagonal peaks. The off diagonal peaks are rise due to the transition from 0 to 1 for the mode 2 also. They can give rise to. And thus, we saw that in the 2D IR, due to the signature of coupling, you get these off diagonal peaks. So if one gets off, wait a second. If one gets off diagonal peaks, it indicates that the modes are couple. Uh, this diagram is more clear to you. For that purpose, I'll just remove the other things. Okay. So now we'll go to the next question. The next question is, in the Febry-Perret interferometer, in frequency domain, the function of the interferometer is to see. In this frequency domain, you use an IR beam that has a high frequency. Sorry, a higher, that is a very fast short pulse of 100 femtosecond. Then immediately there is a splitter. It divides this beam into two parts, the probe and the pump. Now what happens is, see this pump. Uh, it goes straight through a connection of mirrors and passes through the sample. Similarly, there is a probe which passes through the samples. Now, in order to scan the pump beam intensity, you use this FB interferometer. Okay. And this FP interferometer, it can scan a broad range of frequency over it. Okay. So that is why the function of every interferometer is to scan a broad range of frequency. How is this Febry interferometer connected? These are two semi or partially reflecting mirrors. So as the light enters here, it gets reflected in the same way, okay, throughout the mirrors, and then it comes out at some time. So this is called as the cavity dumping, and it is similar to that only. Okay. Now we'll go on to the next question. The question number 9. Question number 9 says, what are the processes that are involved with the biexciton formation? So biexciton formation, we have discussed this in detail in the previous questions, and we got to know that in the biexciton formation, when the hot exciton excites or say ionizes other electron from the ground state, it is called impact ionization. The second case. Second case is after biexciton formation, the electron hole can undergo recombination. In this recombination, see, these two meet together and one exciton with the excess of energy is promoted to further higher level. So this may also happen. This process is called Auger recombination. Apart from this, there is one more that is called the singlet fission, but this is not different from that. Say that this is the energy level gap. This is the some high order SN state. Now, when the SN state from here, the electron comes to the ground state, if the energy of triplet state is lower than that of the second singlet state, then in this case, it may lose energy, come to the triplet state, and then further come to the ground state. This process is called as the singlet fission. Okay. This, although what is our point of interest is the process that includes the biexciton formation is processes that are involved in biexciton formation are Auger recombination and impact ionization. Okay. So, with this, we'll go on to the next question. That is the question number 10. Question number 10 says the fourth part of laser pulse in time domain 2D IR spectroscopy is. So here I have kept a diagram, the time domain of 2D IR spectroscopy. So as you can see in this, there is a lot of complex system. First is this incident beam is split into further portions. Say this at first point of time, this is split between 1 to 2. Second point of time, it is again split to 2 and 3. Then this 2 goes through a system and this 3 again goes through this system. Why are these systems? These systems are present in order to like promote a time delay between each. Okay. Then they pass through the sample altogether, and what you record at last is this dotted beam which comes out of the sample and not any of these three, 1, 2, 3 beams. Okay. And these three beams are like say in the form of square, they are on the each vertices. And the dotted beam is say the sum of the vector sum of the, is a wave vector sum of the individual beams. 1, 2, and 3. Okay. So, what are the options here given to us? A pulse pair is used as pump in time domain so that there is sinusoidal distribution of wavelength. So this is the pulse pair. Sorry. The fourth part of the laser pulse in 2D is the this. This is the fourth part and this is the local oscillator. And it is used for Fourier transformation, which is necessary to extract the electric field data. Okay. So these two are the options for this question. After question number 10, we'll go to the question number 11. A pulse pair is used in the time domain 2D IR spectroscopy. So what is the reason for that? For the Fourier transform. Okay. For Fourier transform, it is used. Okay. Now, so far we have discussed all the 11 questions that are for the assignment of week 12. Now we'll be discussing few more questions which are from the previous assignments, and thus we'll try to solve them. So this will be a quick revision sort of for including all the topics which were discussed. Normally, mainly that whatever questions I have kept, those are the numerical ones. So these are important from examination point of view. So the first one is the average lifetime that is spent by a molecule in its excited state is called. See, molecule in the excited state can undergo various processes. And including these processes, they can include in the form of light or non-radiative. Okay. And the time which this molecule spends in this excited state may not be categorized into radiative lifetime or non-radiative lifetime or most probable lifetime, but the term that can be used is the fluorescence lifetime. So the answer is the average time spent by a molecule in its excited state is called as the fluorescence lifetime. Okay, fluorescence lifetime. Now, this was the question 1. Now we'll go to the next question. The question 2 asks the value of chi square should be. What is the chi-square? This chi-square is something which we studied in data fitting. Okay. And in this data fitting, we got to know that from the decay curve, you can get the value of exponents. Exponential. Okay. And how proper the data is fitted is given by the value of chi-square. And thus, the value of chi-square for a good data should be close to 1 or more than 1. But it cannot be less than 1 or equal to 1. So these two options are incorrect while, oh sorry, this option, I'll just rub it. So more than 1 it can be, it cannot be less than 1, but it can be close to 1. Okay. So this was the second question. Apart from this, in the data fitting, there are other two factors that are considered, that is the residual weighted residual, and second is the goodness of it. So there are certain values, parameters, or this value, especially the chi-square value, that you should be considered when you consider the data fitting or when you do the data fitting. Okay. Now we'll go on to the question number 3. The question number 3 says the wavelength of light that is obtained by adding the two beams of frequency 420 and 740 nanometer is. Okay. So first of all, see, in order to add these, we need to convert the two into some value of energy, because energy can be added or frequency, but you cannot find out the wavelength by adding up these two wavelengths. So first we'll convert the wavelength to energy. Okay. So we'll write this as hc by lambda 3, which is formed of the energy of the wavelength of light that is formed by adding these two, is equals to hc by lambda 1 plus hc by lambda 2. Now what we'll do? hc will be common, so it will be 1 by lambda 3 is equals to hc 1 upon lambda 2 plus 1 upon lambda 1. hc and hc will just cut and cancel out each other, and what we'll get is 1 upon lambda 3 is equals to 1 upon 420 plus 1 upon 740. Okay. Now we'll just multiply 420 into 740. 740 plus 420. Okay. And then we'll just find out the answers. Yeah. So the answer that would be is approximately 268 nanometer, and accurately that was 267.93 nanometer. So the answer to this would be 268 nanometer, and it lies in UV range of light. Okay. So this was the third question. Simply we have to add the values of each, and by adding the values of each we can get to know that how it will be. Okay. And it lies in the UV range of light. This UV is not proper, so I'll just write it properly. UV means ultraviolet range of light. What you have to do, just convert the value to in terms of energy, because anyway if you just add up the wavelength it will not give the correct answer. So you have to convert it into wavelength, and then you have to just solve simply by simple maths and take the reciprocal of lambda 3. So what I have done here is it came to be 1160 whole upon 3.10 into 10 to the power 5. And then what I did was divided each and then took the reciprocal. So we got the answer easily. Okay. Now we'll go on to the next question. That is the question number 4. The question number 4 function of the dichroic beam splitter is. Okay. So what is the function of a dichroic beam splitter? So dichroic beam splitter is used to split two beams. Okay. Split two beams means split two beams means suppose this is your dichroic beam splitter. Okay. Now you have the light of two frequencies, say mu naught, mu s. What it does is it transmits mu naught and it reflects mu s. And in this way, the two light beams are separated from each other. Dichroic beam splitter has the same function. So here I'll just write it in. Okay. Now, function of a dichroic beam splitter in this case was separate the excitation light from the fluorescence light, fundamental from the second harmonic, some frequency from fluorescence. Or so basically, here we studied this whole in case of an instrument, and thus in this case the answer could be fundamental from second harmonic. But basically what we need to know is the dichroic beam splitter is simply used to split two beams, uh, and that can be any two beams of your choice. Okay. uh, then now we'll go on to the next question. The question number 3. A TCS-PC experiment is carried out by a TAC range of 50 nanoseconds and an MCA gain of 8000 channels. Temporal resolution they have asked, and temporal resolution in the unit of picosecond per channel. So for this, simply temporal resolution means resolution at time scale. Okay. Now, see, overall, the more the number of channels you take, the better resolution you get. Okay. So, what you can write here is the more the number of channels, the better the resolution. Okay. And in our case, if you want to calculate the temporal resolution in picosecond per channel, so we have an option. We are given the TAC range. The TAC range covers of 50 nanoseconds and there are 8,000 channels. The only thing we have to do is convert nanosecond to picoseconds. So nanoseconds to picosecond, 1 nanosecond is equals to 10 to the power 3 picoseconds. Thus, solution comes to be 50 into 10 to the power 3 whole upon 8,000. So it comes to be 50 into 10 to the power 3 whole upon 8 into 10 to the power 3. So it will come somewhere in the range of 6.2, no, 6.3. Yeah, 6.33. Okay. So it will come to be 6 point, no, no, 6.2, 6.25 picosecond per channel. Okay. Is similarly, if we take the value of, if we increase the number of channels, what our point was, if you increase the number of channels, so taking the same range of 50 nanoseconds per, say now we have taken, instead of 8,000 we have taken 12,000 channels. So then how it will change? It will come to be 50 into 10 to the power 3 whole upon 12,000. So it will come to be 50 upon 12, and thus 50 upon 12 is, so the answer would be 4.16 picosecond per channel. So each channel is taking the reading of only 4.16 picoseconds. The resolution has increased quite a bit. Okay. So our point is right. The more you take the number of channels, the better resolution you get. And if you want to calculate the temporal resolution in picoseconds per channel, just divide by. Okay. Now, uh, so far, this was what was the number of this question. This was the fifth question. Okay. Now we'll go on to the next question. The next question is, a horizontal beam of pulsed laser light is reflected by a retroreflector. In order to bring about a delay of 10 femtoseconds in reflected beam, the retroreflector has to be moved by. Okay. So, a retroreflector is something which we have studied, like it is a system made up of two glasses, two mirrors, which is used to bring a delay in the lights. Okay. Now there is a horizontal beam of laser that is going on straight. It moves through this path and it goes straight back by reflection. Retroreflector, what it does is increasing the path length. Retroreflector increases the path length of beam to increase the time delay. Okay. Now, you want a delay of 10 femtoseconds. So, delay should be of 10 femtoseconds. According to that, you can measure the distance by which the retroreflector can be moved. Okay. So the retroreflector has to be moved. Now there is a laser beam. Since it is a light, it will have a velocity equal to 3 into 10 to the power 8 meter per second. Right. Now you need to know the distance which will bring 10 femtoseconds of delay. So the light has to travel that much distance. Now you are considering that this is the path. So this it has to travel x and x. That is the distance should be, that is the distance is 2x that it has to cover. Okay. Now with this distance, how much time it will distance upon time is equals to speed, right? Velocity of light. Now, how much distance it has to be moved? That will be double the distance between this point and the light. Okay. So, what you will do is just take the velocity of light of 3 into 10 to the power 8 meter per second. Then you take the time. That is the 10 femtoseconds. Now, I'll write this in a clean way. So, distance is equals to 3 into 10 to the power 8 meter second inverse. Right? Now, delay is of 10 femtoseconds. See, 1 second is equals to 10 to the power 15 femtoseconds. So, you have to convert this into distance upon time. Now, so you have to find distance, you need to multiply it with time. Is equals to 3 into 10 to the power 8 meter second inverse multiplied by 10 into 10 to the power minus 15. Okay. So it comes to be 30 into 10 to the power minus 7. Right? Or wrong? 30. 3 into 10 is 30. 10 to the power minus 7. So it will be 3 into 10 to the power minus 6. By this distance, yeah, this should be the total distance. So we have to found out that distance, or else we'll write here 2x is equals to 3 into 10 to the power minus 6. So what will be the value of x? The value of x will be 3 into 10 to the power minus 6 whole upon 2. So it will come to be 1.5 into 10 to the power minus 6. And as we know that 10 to the power minus 6 means 10 to 1 micrometer. 10 to the power 6 meter is equals to 10 to the power 6 meter is equals to 1 micrometer. Thus, our answer will be 1.5 micrometer. So, this will be our answer. Now, suppose I give you that the retroreflector, retroreflector needs to bring, has changed by say 4.5 micrometer. Okay. The retroreflector is moved by 4.5 micrometer. So then what will happen? If it is moved by 4.5 micrometer, then this is 2x, this is x. Okay, so the total distance would be 9 micrometer, right? Because I have told that the retro reflector has now moved by 4.5 micrometer. So the total distance that light will travel is double of it. For the calculation purposes, we have omitted this value, this particular value. So 4.5 into 2 you will do. So it will come to be 9.0 micrometer. Whole upon time is equals to distance upon time is equals to speed 3 into 10 to the power 8. Thus, to find time, you will just what you will do? You will do 9 into 10 to the power minus 6 whole upon 3 into 10 to the power 8. This is meter second inverse. This is meter. These two get cancelled. What you get is 3 into 10 to the power minus 14 seconds. Or if you want to convert to femtoseconds, that is 30 femtoseconds. So the delay will be of 30 femtoseconds. So how much delay is done? The delay that the retro reflector has created is of 30 femtoseconds. Or else I'll just write it in a clean way. Delay of how many seconds? 30 femtoseconds. And answer to this question is 1.50 micrometer. Okay. Now we'll go on to the next question. This was the question number. This was the question number 6. Okay. Now we'll go on to the next question. If M0 is the refractive index of intensity of light of low intensity, is the refractive index of light of low intensity, then the relationship between the refractive index N2, this is not this is N2 and intensity of light I is. Okay, and this is N0. So the relation that you get from the intensity is N0 is equals to, N is equals to N0 plus 2R. Okay. So refractive index of light depends on the intensity of light. The higher the intensity of light, the more will be the change in refractive index. So the change in refractive index can be written as N0 is equals to N2 plus I. Thus, we can write as N0 directly, not N0, N directly depends on the intensity of light. Okay. So it directly depends on the intensity of light and it is given by this. All these relations are not correct. Okay. Based on this, we can also say that the refractive index for the high intensity light is quite high. Okay. And if the particular light moves from the high intensity region to low intensity region, it moves away from the node. Now I'll just give you one more question. We have some space left. Yeah. So on this page only we'll discuss another question. The question is, what is the expression for fluorescence quantum yield in terms of absorbance? If the intensity of transmitted light is IT. So basically, the fluorescence quantum yield is given by phi f is equals to intensity of emitted light or transmitted light upon intensity of absorbed light, right? Now, here you are given intensity of absorbed light. Suppose you are not given intensity of absorbed light and you have to write in terms of absorbance. So, absorbance is equals to log of I naught upon IT. Now, see, since we know that the IT can be also written as IT is equals to I naught minus IA, you can write log of I naught upon I naught minus IA. Taking out A common, sorry, I naught common, you can write that, yeah, A is equals to, or say 10 to the power A is equals to I naught upon I naught minus IA. Taking this common I naught into 1 upon 1 minus IA. Okay. And this is equals to 10 to the power A. Now what if I write this to be as 10 to the power minus A upon is equals to I naught 1 upon I naught 1 minus IA. Okay. So 1 minus IA upon I naught. So here then we'll write it as, or we'll just write it I naught minus IA upon I naught. So by 1 minus IA upon I naught. So it will come to be as 10 to the power minus A is equals to I naught bracket 1 minus IA upon I naught. Okay. And then what we'll do, it will be 10 to the power minus A upon I naught is equals to 1 minus IA upon I naught. Then we'll shift it to here, the RHS side, IA upon I naught is equals to 1 minus 10 to the power minus A upon R. Okay. And then what we'll do is, the value we'll get is, final will be IE upon I naught into 1 minus 10 to the power minus A. So this is the final value which we'll get by solving this. Okay. So I think there is some problem in this calculation. I'll just repeat that. Erase it and write it again. So here, from this calculation, we got that we'll just substitute the value of IA here, and what we'll get, phi is equals to IE upon IA is equals to IE whole upon I naught into 1 minus 10 to the power minus A. So this relation is quite important because questions may be asked from this also. Now, uh, with this, we have solved many questions which are from previous assignment also, which are from this assignment also. And uh, so, with this, we are going to end our session. Thank you so much, everyone, for joining. And I'll just end the class.